Hello, everyone. Thank you very much for the invitation to present to you today. I am sorry that I could not be there in person. Um, so I'm going to be sharing with you my recent work on trying to design and control robotic prosthetic legs for above-knee amputees, as well as exoskeletons for individuals who have partial impairments of their lower extremities. So this work was done at the University of Michigan and previously at the University of Texas at Dallas. And so before I start though, I want to first point out that we have a PhD and master's degree program in robotics at the University of Michigan. And so please consider us if you know people that are thinking about going on to a master's or PhD degree and are interested in robotics. So I want to first motivate the problem that I'm working on. And so thinking first and foremost about above-knee amputees, using conventional prosthetic legs, these individuals tend to walk slower, they tend to fall more frequently, and they tend to spend more metabolic energy walking from point A to point B than able-bodied individuals do. And this is because conventional prosthetic legs simply don't reproduce the biomechanics of the missing limb. And so that's where robotic or powered prosthetic legs have potential to restore the missing function of the musculature of the amputated limb and therefore restore natural and confident locomotion. Now, I first want to discuss how powered prosthetic legs are typically controlled. And so something you have to keep in mind is that robotic or powered prosthetic legs are still very new and still very much in the research stage. In fact, there's not a single commercialized powered knee and ankle prosthesis on the market. There's a couple individual powered joints that don't really work well together, and they haven't really been highly successful. And so one of the big challenges associated with these devices is that when you introduce sensing and actuation, well, then of course you have to introduce control. And these devices can be quite complex. And so, especially with the range of behaviors that have to be reproduced to mimic human walking. And so the typical approach to doing that is to look at the human gait cycle and try to characterize it as a sequence of events or a sequence of behaviors, starting from heel contact, push off, and to knee extension, and then repeats. And so in the conventional approach, we typically define a distinct controller for every one of these behaviors. And so every one of these states here in this finite state machine would have its own set of control parameters. And you'd also have switching rules that go from one state to the next. And those also have parameters that they depend on. And the big challenge then is that a lot of these parameters are patient specific. And so one set of parameters that work for me won't work for you. And so then you end up having this tuning problem where you have dozens of parameters that you have to potentially tune for every individual. It takes hours, sometimes days to do this correctly to get really natural walking. And so this is not a clinically viable solution. And it gets even worse when you start thinking about multi-activity control. And so you might have a higher level task state machine where every one of these states here representing a task has its own set of phases and controllers associated with them. And so you end up having hundreds of control parameters, and this thing is extremely complicated. So my approach to solving this problem is to leverage control approaches that are emerging in the field of walking robots, which I know is of interest to many of you in the audience. And so trying to use these principles that can get an autonomous robot to walk correctly, then apply that to controlling a robotic prosthetic leg to allow a human to walk naturally, apply that again to exoskeletons, and then once we can do this and help humans walk, then of course we've learned something that we can use to make robots walk more human-like. And so I think of this as this nice cycle of one discipline informing the other and vice versa. And so the inspiration we take from robot walking is this concept known as a phase variable. And so this video here shows the robot Ernie at University of Notre Dame. As the researcher pushes the boom forward or backwards, Ernie's measuring his hip position in space, and that tells Ernie what his progress is in the gait cycle. And so it tells him whether he's moving forward or backwards, which then allows him to control his hip and knee joint to synchronize to that progression in the gait cycle. And of course, if you give it a push, then it can walk in a normal fashion. And so this idea originates from Professor Jesse Grizzle here at the University of Michigan. And the idea is that if you can find some mechanical signal that is measurable, that evolves monotonically over a steady gait cycle, well, then you have a one-to-one relationship between time and the phase of the gait cycle in a continuous sense. And if you have this monotonic relationship, then you can replace time with this mechanical representation of phase. And so you might be able to reparameterize this desired joint trajectory to be a function of phase rather than time. And so that if you're walking and then suddenly you grab the robot and you hold it, call this a phase shifting perturbation, and then the phase variable will stop moving forward. And so then if you're controlling the robot according to the sense of phase, then the joint angles will just freeze because the phase progression has frozen. And then if you let go of the robot and it continues, well, then it'll restart where it left off. And if this is a perfectly phase shifting perturbation, then you don't see any transient effect whatsoever when viewing the gait cycle over the phase variable. So this is how you're able to have a robot maintain synchronization to its forward or backwards progression. All right, so now we have to be able to apply this to human walking. So we have to be able to measure such a variable from the human body, preferably with sensors on board the prosthetic leg. And so after looking at a lot of different signal sources, we eventually converged on the thigh angle, which is a global measurement of the angle of the thigh with respect to gravity. And what's nice about it is that it has this sinusoidal pattern. So over time, every gait cycle, it's going to repeat as a sinusoid, which means you can build something called a phase oscillator from this. And so it tells you where you are in this cycle that repeats exactly every stride. And so this gives us the opportunity to measure the progression of the human from, say, an inertial measurement unit attached to the top of the knee joint, which is then connected to the socket or the residual limb of the amputee. And so now that we have the sense of phase, we have to think about how we're going to actually control the joint patterns. So where do the joint patterns come from in the first place? And so what we've found is that taking able-bodied data and parameterizing it as a function of phase is a really good starting point. This gives us a pretty decent walking for all of our human subjects right from the get-go. But this, of course, isn't optimal for any particular person because we all walk differently, right? And so that's why we have this user interface that we've developed that allows a clinician or a researcher to be able to drag these control points to modify the trajectory in real time, and then re-encode the output function as a function of the phase variable. Essentially, this just corresponds to our desired joint angle as a function of phase. Then we can define our error function. So this is the measured or real joint angle, and this is the desired. And then we can do any number of control techniques to drive this error signal to zero. In most of our work, we just do proportional derivative control because it's model free. And it also, depending on the actuators you have, this can actually be the same thing as impedance control, which is nice when you're interacting with a human. And so having that paradigm for designing trajectories and the control outputs, we then implemented it in our first generation robotic leg, which we built in-house. And it's a little bit of a, we call it the Frankenstein leg. And it was our first try at it, but it was able to get the point across, which was exciting. So again, there's the inertial measurement unit that is attached to the top of the knee joint. And it has an actuated knee and an actuated ankle. And I want to point out right now that the actuators are highly geared, which means they're going to be very loud and noisy and very stiff. And we're going to talk about that later and address that later in the talk. So this video shows a participant becoming acclimated to the leg for the first time. So he starts trusting that the leg is going to move and place its foot where he expects it to, based on what he's learned about this mapping from his hip angle to the foot position. So again, it's just he's controlling his hip angle, which is being measured by the IMU, which is then synchronizing the knee and ankle angles to the appropriate place in the gait cycle. And then this allows him to do this very natural stepping motion. And of course, we can do walking. And so this shows a comparison between the take-home passive leg and the robotic leg. Okay. And you can also do backwards walking. But you'll notice that he's taking much longer steps walking backwards with the robotic leg because, again, he's able to trust that the foot will plant where he expects it to be, whereas with the conventional leg, it's just a passive hinge joint, and there's no guarantee that it'll be able to bear his body weight if he takes a full step backwards. And then we're able to do very natural transitions as well, because of the fact that it's fully synchronized to this motion. Now, this is a scenario where he's crossing an obstacle. And so essentially, again, because he's learned the mapping from his hip angle to the foot position, he's able to control the foot position enough to get it over the block reliably, which is something that was much harder to do with the conventional leg. And we're able to do fun things like kicking footballs and so on. And of course, we can walk continuously at different speeds. In fact, the phase variable can automatically adjust walking speed because of the fact that the hip angle will be moving at the rate at which the user desires, which means that the prosthetic leg will stay synchronized to that hip angle. And so what we noticed is that with one session, we were able to observe noticeable reductions in amputee compensations in the intact joints. So essentially, when walking with a conventional prosthetic leg, amputees tend to compensate for the fact that the biomechanics are not completely natural with the prosthetic leg. For example, the leg does not provide positive power. It cannot propel or inject energy into the gait. And so the hips and the sound side have to do all that. And so that results in compensations like hip circumduction and hip hiking and ankle vaulting. And we noticed after one session that the powered device actually has a noticeable reduction compared to the passive device in its circumduction and hip hiking and ankle vaulting. Now, these compensations aren't eliminated completely, but it's going in the right direction, and we believe, we hypothesize that with additional training, some of these compensations can be unlearned to allow more natural walking. Now, I briefly mentioned earlier that our first generation robotic leg was very stiff, very rigid because of the use of a very high gear ratio. And so with our second generation leg, we kind of took the exact opposite philosophy. We ended up embracing a quasi-direct drive philosophy, much like the MIT Cheetah and other recent legged robots that have seen really great performance using high torque pancake style motors and very low gear ratios. And so in fact, we use a 22-to-1 gear ratio, which allows the device to be very back drivable. So you can see here that the researcher is able to very easily move it when it's powered off. It doesn't have very much resistance to it, has very little reflected inertia, very little friction or damping. And so the benefit of this is that you get quite natural walking. You get nice compliance to ground impacts. So the foot actually is able to kind of roll more naturally as you walk. We also get very fast transitions from the high torque required at push-off to the high velocity required at early swing. And that's a nice feature as well because it has very high bandwidth. And so you can see this better in this video. So again, has nice powered push-off, which helps propel the leg into swing, and nice compliant impacts. And also very pendular knee swinging motion, as if the knee joint was a passive pin joint during swing, but then you of course get the benefits of the power during stance. Okay, and so we did a brief amputee outcome study with 3 above-knee amputee participants, and the results were not entirely consistent, but for the most part, we saw very positive trends. So in particular, we saw increased push-off power for 2 of our 3 participants compared to their conventional leg. So essentially, one of our participants just didn't trust the leg to stay in stance phase long enough to get the push-off that it provides. And so if you lift the foot up too early, then you don't get that push-off. And so that's what we observed with one of our participants. We noticed that with all participants, we had an increase in stride length. And for the participants who embraced the powered push-off at the ankle, we saw a decrease in the hip power for pulling the leg into swing, which is really important because that's one of the sources of metabolic cost because they have to lift the leg into swing phase because of the fact that with a conventional leg, it doesn't help push off. And so then the consequence of that is that we had less residual hip work per stride with the powered leg compared to the passive leg. And this was pretty consistent across all subjects, which is really exciting. And so now what we're working on is we're trying to extend this control paradigm using this nicer hardware into a continuous task paradigm. So previously we talked about how you have a continuous sense of phase. And so we didn't really talk about how to deal with task transitions. And so one way you can think about it is that you still have this high level approach of having a task classifier that chooses, or a task state machine that chooses which task you're in. And then within each task mode, you have your continuous phase controller. But we want to begin to merge these 2 levels of control into one so that you're able to do continuously varying activities. And so our idea here is that we're going to try to extend additional dimensions of our kinematic model, where previously we had just the phase variable as the independent variable and the joint angle as the dependent variable. But now we're going to add task variables to that. And so we're talking about having walking speed, ground inclination, maybe transitions between stairs or not walking on stairs. And so you can imagine that in this activity space, you can have any point in this 3-dimensional space could represent your activity. And so you can have any real number for speed, any real number for slope. And we have a kinematic model that tells us what the joint angles should be as a function of these task variables and our sense of phase as well. So that is ongoing work. And so in closing, I want to just talk about how we're also using these ideas for exoskeletons. And so in particular, all of the commercially available FDA approved exoskeletons, at least in the United States, that have been approved for use in clinics and at home are primarily targeted towards spinal cord injury. And so they are designed to do everything for the lower extremities because the individual has lost most or all control of the lower extremities. Now, what we're interested in doing is something a little bit different. We're interested in partial assistance. And this is for individuals who have some residual control left over, or maybe full control, and just are trying to maintain endurance. And so in the case of stroke, maybe there's some residual control left over, but they're weakened. Osteoarthritis, maybe they have good control, but then they have to deal with pain and maybe some atrophy due to that. Advanced age, We have to be concerned about weakness and fatigue as well, and also with repetitive overuse injuries are often caused by weakness or fatigue, leading to risky maneuvers like bad lifting posture. And so we're trying to use the quasi-direct drive actuation paradigm that I talked about earlier in the realm of exoskeletons, so that we're able to allow the human to very seamlessly control their intended joint kinematics while getting torque assistance in a task invariant way. And so we're doing things like gravity compensation and inertial compensation, so that the control method does not depend on any trajectories whatsoever, which allows the participant to have, again, full control over their kinematics in an assistive environment. So that's also ongoing work. And so in closing, I want to thank you for your time and acknowledge the funding agencies, the NIH, the NSF, and the Bros Welcome Fund, as well as, of course, the fantastic students and staff who have contributed to this work. And so now I'm happy to answer your questions. Thank you very much.